In this video, we're going to have a look at some of the restrictions on permutations. Our first one is called the grouping technique. So this is how many arrangements we'll have when two or more objects are actually grouped together. So let's use our example with the word maths. So we know that if we consider all letters being used once with no restrictions, then we have 5 factorial ways of arranging these letters. So that will be 120 ways. However, how many arrangements would be possible if the letters A and H must be together? So what we want to consider, if we go back to our little rectangle with our 5 spaces, we want A and H to be together. So what we're going to do is consider A and H to be one unit. Okay, so we're going to call that one unit. We're going to bind them together. So now, instead of 5 objects to arrange, we only have 4 objects to arrange, and then we can place them. So 4, 3, 2, 1. So with A and H being together, we now have 4 factorial. But what we also need to consider, do we place the order of that unit as AH or HA? So in fact, if we take the single unit, we have 2 factorial ways of arranging those 2 letters that must be together. So we can add that onto our calculation. So we end up with 24 times 2, so 48 arrangements. So this significantly reduces our original 120 arrangements when we don't have any restrictions. There's a nice little summary here that says if we have n different objects, so we had 5 objects, and we arranged them with R objects adjacent or next to each other, so that we had 2 objects that needed to be together, then it would be n minus R plus 1 factorial times the R factorial. So we've got 5 take 2 is 3 plus 1 is 4, so this is our 4 factorial times our 2 factorial. So that's a really nice sort of summary calculation. But I often use a bit of common sense and our lovely diagram to help us understand how this actually works. So let's take a look at this little question here. 6 files, A, B, C, D, E and F, are to be arranged on a shelf. How many ways can they be arranged? Well, there's no restrictions here, so we've got 6 files, so that would be 6 factorial, which is 720 different arrangements of those files. How many of these arrangements have files A and B next to each other? So if we consider those 6 files, we're going to group 2 of those files together. So we've only got 5, 4, 3, 2, 1 factorial. So we've got 5 factorial, but those can either be arranged as AB or BA. So we've got 2 factorial arrangements. So that leaves us with 120 times 2, so 240 ways, which is certainly a reduction from the 720. Let's take a look at another question. We've got Fred, Finn, Fran, Faye and Faith to be arranged in a line for a photo. How many arrangements are possible if Faith must be on the left? So because we've got 5 people here, we know that Faith has to be on the left, and then the rest may be arranged in 4 factorial ways. That's just 24 ways. How many arrangements are possible if Faith is on the left and Finn and Fred are next to each other? So I'm going to draw that rectangle again with my 5 spaces. So we're going to put Faith here, and we're going to put Fred and Finn together. So I'm going to group them into one unit. So now I've got 3, 2 and 1. So I've got Faith, her position is set. We've got 3 factorial ways of arranging, but remembering that Finn and Fred have 2 factorial ways of being arranged in their group together. So that leaves us with 12 ways. 1 times 6 times 2. So this is called the grouping technique, where things will go together, and that could be 2 or more objects. Our next restriction is called the complement rule. This the use of the word complement reminds me of the probability of being the complement of a set A happening would be the complement of it not happening, and that's exactly what this is talking about. The complement rule allows us to find out how many arrangements when 2 objects, and only 2 objects, no more than 2, are to be apart from each other. So it's exactly the opposite of the grouping technique that we've just done. So using our example of the word maths, we know we've got 120 ways they can be arranged without restriction, and A and H together reduce it to 48 ways. So let's consider now, if A and H have to be apart, this would be the complement of them being together. So to find that, we can take the total without restriction, which we know is 120, and subtract the number where A and H are together, which we found to be 48, and that will leave us with 72 arrangements. So if we take a look in general, if we have n objects in which we have 5, and we're going to arrange it with 2 specific objects apart, so we're going to do only 2, then we can come up with this general rule here, which says it's going to be n factorial, so for us 5 factorial, subtract 5 take 1 factorial times 2 factorial. Now if we take a look at this, this is the number in the total, subtract the number of them being together. This was when they were grouped. And that's how we can arrive at our solution for the number of arrangements. Let's take a look at another example. So we've got Josh, John, Jenny, Jake, Joe and Judith. So that's 1, 2, 3, 4, 5, 6. People are, they're actually new reindeer apprentices in the North Pole. During their single line practice flights, Jake and Jenny must be kept apart as they keep fighting and won't fly. So how many ways can we arrange the reindeer? Now, rather than drawing a rectangle of 6 and trying to work out all the different ways that they could be apart, which would be quite a lot, we can make it easier on ourselves by working out Jake and Jenny being together and then taking that away, so using the complement. So the total number of arrangements with no restrictions would be 6 factorial, which is 720. The number where Jake and Jenny are together, well, we know that that would reduce our group of 6 to a group of 5, so 5 factorial, and then Jake and Jenny can be arranged either way in that group. So that would leave 240. So if we want Jake and Jenny apart, we can use the complement, which is the total, subtract all the arrangements where they're together, and that will leave us with 480. We're going to have a look at 2 more restrictions that we often come across when we're looking at different arrangements. So we have how many different 4-letter words can be formed using the letters from the word number, where no letter can be used more than once if there are no restrictions. So there's a couple of ways that we can look at this. We've got 6 letters here, so we could say 6 permutate 4. We could use our calculator, or we know that we could do 6 factorial over 2 factorial, and we're going to get 360. Remember, our other option is to think about placing those letters into those 4 positions. So we'd have 6 times 5 times 4 times 3, and that'll always give us 360. Words must start and end with vowels. So if we consider that group of 4, must start and end, so we're looking at the first and last position. There are 1, 2 vowels in our word, so we can use 2 factorial to represent where those 2 vowels go. We've got a choice. And then the other letters we've got 4 of them left, so we can have 4 and 3. So we've got 2 times 4 times 3 times 1, which is 24 different arrangements. How many are possible if the second letter must be N? Nice and easy. N must go here, and then we've got 5 letters left that we can arrange. So we've got 5 times 4 times 3, which is 60 different arrangements. In our last example, we've got a 5-number code must be made from the digits 0 to 9. How many possible codes can be made if any digit can be used more than once? So what that means is, in our 5-number code, we've got 10 digits that can be used as the first number, 10 for the second, and so on. So we've got 10 to the power of 5, which is 100,000 different possible codes. How many codes are possible if the code must be even and we can only use each digit once? Okay, so we're going to focus on this last one. From the digits 0 to 9, there are 5 digits that we can use that are even. Once we've used that one, we've got 9, 8, 7, and 6 digits left to use, and we can use the multiplication principle here to find our answer of 15,120. The code must start with 5, end in a 3, and not repeat any digits. So, start in a 5 and end in a 3. So those numbers are set, so we can't use those 2 digits, so we're down to 8 digits. So we've got 8 times 7 times 6 arrangements, and that will give us 336. How many possible if the code is an odd number larger than 60,000 using the digits once? So here we have to think about that it can start with 60,000, 70,000, 80,000 or 90,000. Now 70,000s and 90,000s are odd. So I'm going to just treat 2 groups separately. I'm first going to have a look at those that start with 6 or 8, because all the odd numbers can go in the end. So I've got 5 odd numbers to choose from, and 6 or 8 to be the starting number, to be at 60,000 or more. And then that I've used 2 numbers, so that leaves me with 8, 7, and 6. This gives me a total of 3,360. Or, which we know means add, let's consider if it starts with a 7 or a 9. That is going to affect how many odd numbers we can use. So if it starts with 7 or 9, I've got 2 numbers to choose there, but once of those odd numbers is used, I've only got 4 odd numbers left to put at the end, and then I've got 8 and then 7 and 6 digits left. This gives me 2,688. So in total, I have 6,048 different arrangements. So this question is a little bit more involved, and it's nice to be able to pull it apart or partition it to consider the different starting and ending numbers. So in all of these restrictions on permutations, it's really important to remember that we're using that multiplication principle to help us out, but we always should consider the restriction first.